gentlemen, today we're going to learn about magnets. Now, magnets, they are pretty cool. They almost seem magical at times, and the physics behind magnets is no different. So let's dive in. All right. So in order to learn about magnets, first you need to understand that the idea that magnets, they do a very good job of attracting or repelling, and they can do one or the other, and it all depends on what the magnet is near. So if another magnet is near another magnet, you have two choices. Will it attract or will it repel? So if you've ever heard of the phrase opposites attract, that's the same for magnets. Much like electrical charges, where we have a positive and we have a negative charge, they attracted each other. In a magnet, a north pole and a south pole will always attract to each other. Now, much like negative charges and negative charges repelling each other, or a positive charge and a positive charge repelling each other, the same is true for magnets. A north pole near a north pole will repel, and a south pole near a south pole will repel. No exceptions. And we have a little infographic down there if you want to take a look to see exactly what happens. If we have a south with the north, it will always attract. No other exceptions. In no other case will another magnet attract another magnet. All right, so the reason why do magnets attract or repel? And that's because magnets are surrounded by what we call a magnetic field. Okay, so we're hearing a lot of similarities talking about magnetic fields, electric fields, and like charges and unlike charges, like poles and unlike poles, and there's a very strong reason for that, and we'll get into that in some other videos. So a magnet is constantly surrounded by a magnetic field, and these fields, much like electric fields, the magnetic field can exert a force. It can either push or it can pull away on different substances. All right, so we're going to learn how to draw magnetic fields. So what you see on your screen is a bar magnet. One side is north, one side is south, and over on top of the bar magnet are iron fillings. And iron is very magnetic. And if you know the symbol for iron, which is Fe, that comes from the Latin root ferrous, which is iron. Okay, and that's where we get the term ferromagnetic. Cool. So the cool thing about the iron fillings is that they do a very good job of showing the magnetic field. You don't see the arrows in the field because magnetic fields are vectors, but you do get a good sense of how the magnetic field are all interconnected. Now, to me, it kind of looks hypnotizing. So let's move on to the next slide. All right, so in nature, this is a red onion. Now, red onions are not magnetic, but I just wanted to show you this picture because this picture to me, if you kind of take a look at the middle area, it kind of looks like an onion. So, boom, in case you have a test question that asks you to draw the magnetic field of a single bar magnet, you can be like, ooh, bar magnet, red onion, ace. All right, here's the rules to drawing a magnetic field around a single magnet. The vectors always come out of the north and into the south. I'll repeat that one more time. If it's anything that you need to memorize, remember one or the other, okay? Out of the north or into the south. If you memorize one, it's always going to be the opposite for the other. Out of the north and into the south. Now, what I mean by out of the north is if we take a look at these graphics down below, the vector heads or the arrowheads are coming out of the north and the vector arrows are going into the south. All right, now this is very similar to the positive and negative charges. For the positive charges, all of the electric field lines came out of the positive charge, and for the negative charge, all of the field lines came into the negative charge. And the same goes if you're thinking that north is positive and south is negative, it's just like that. Okay, and magnetic fields are very three-dimensional. We draw them two-dimensional, but they are surrounding the entire magnet. So in order to represent that, we always draw the magnetic field, making continuous loops all around the magnet. And of course, these continuous loops need to have arrowheads because they are vectors. All right. Sometimes the magnetic fields will be shown going through the magnet, and that's actually very important to know because magnetic fields doesn't begin and end at a finite location. It is continuous, and we get to see that whenever we do the iron filling drawings. You can see the magnetic fields going through the magnet. And the picture on the left does a great job showing that concept of the magnetic fields going through the magnet. All right, attraction. So when I take a look at this picture, I see two ends of a magnetic pole, and both of those ends they kind of look like they're connected, right? It looks as if there's rope connecting the two poles together, and that's because they are in fact attracted to each other. All right, so there's gonna be a lot of drawing in this unit. So what I want you to do is after I go through my explanation, pause the video and give it a sketch. But listen to my explanation first. All right, so here we have two bar magnets. We have a bar magnet on the left and bar magnet on the right. The one on the left has a north side that is near the south side of the opposite magnet. So north side here, south side here. And if you remember your rules, remember opposites attract. So the north end of the magnet is attracted to the south end. And using our rules, we know that the vectors always come out of the north into the south. And so this picture does a great job showing us that. Wow. Okay. But the magnetic field doesn't only exist between the two magnets, it also exists around the other poles. And so this picture shows us a great representation of how that happens. And of course, be very mindful of the arrowheads. Good. All right, so pause this video and give this a quick sketch. All right, now this next picture shows us a great picture of magnetic fields repelling each other. It kind of looks like there's things that want to interconnect, but then the laws of physics says no, and so they can't connect. Instead, they're repelling away. They're pushing away from each other. All right, so once again, let's take a look at this magnetic picture. We have a north end and a north end. They want to interact, but they can't because they're too similar, and so we see the magnetic fields coming out of the north, but they're repelling. Out of the north, but they're repelling. And here we have this lone, they want to interact, but the artist just did a very good job showing that the two poles are just colliding. Okay, they don't want to be one. They're butting heads. All right, so pause this video and sketch this image. All right, so here we have a picture of more iron fillings and bar magnets, the red side being the north and the blue side being the south. So we get this really cool image of the north and the south sides here being attracted, the north and the south sides here being attracted, the south and the north being attracted, but then we get the south to the south and this north to the north right here. All of those field vectors are adding up and they're canceling out. So it's zero. So what you're seeing is magnetic field zero. Wow, that's really cool if you ask me. All right, so let's take a look at the fields. We've been talking about fields, so let's look at the general rules for fields. All right, so first of all, you've heard me say it, but magnetic fields are vectors. Okay, so magnetic fields are things that scientists they came up with. It's a tool for physicists to understand the natural world. We call them fields, and the magnetic field is something that magnets create. We draw fields as continuous vectors. So what that means is that the line is continuous. There's no breaks. But sometimes we can draw magnetic fields as broken up vectors. The closer we are to the magnet, the longer the vectors will be, and that just means that it's stronger. Okay, if you draw a longer line, that means the magnetic field is stronger. The shorter line means that it's weaker, much like the electric field lines that we've drawn. And also, just like that, if there are more field lines close together, that means the electric field, or the magnetic field, excuse me, it's stronger there if there's more vectors bunched up next to each other. All right, so let's take a look at this picture. You can see here in this image, these are hundreds of, maybe not hundreds, maybe 100 amounts of magnetic field lines that we see. And we can see that out here, the vectors they're tiny. They don't even look like arrows. But if we take a look here, they're a lot longer and they actually look like arrows. So my question to you is, well, can you actually locate the poles? Do you know which side is north, which side is south? Pause the video and look at the image and think about it. Okay, so I hope you got it right. Just follow the rules, right? The magnetic field vectors come out of the north, so we can see the arrowheads coming out of the north, and it goes into the south. All of the arrowheads are going into the left side. Cool, physics. All right, and this is true if we get hundreds of compasses and we put a bar magnet right on top. We can see the field, the magnetic field, with the compasses. And so the cool thing about this is that the compass will align itself to the magnetic field. Meaning that if we were to draw it, we would draw the arrowheads pointing to the left. We will draw the arrowheads going into the left side of the pole. So the arrowheads are going into the left side of the pole. That must mean that the left side of the pole is, you guessed it, the left side of the pole is in fact south, and the right side of the pole, or the red side, is the north, because the arrows are coming out of that side of the magnet. Cool. All right. So a couple of quick facts about compasses. The compass will always point towards geographic north. Notice the keyword geographic north. So if you're stuck in the woods and all you have with you is a bubble gum wrapper and a magnet, and you need to get to Canada, right? Because we're in the United States. Or if you need to go to the North Pole, if you follow your compass, eventually you'll get to the north, right? Because the compass will point to the north. And it's important to know the compasses are magnetic. Okay, so keep that in mind. So what does this mean in terms of the Earth. Is the Earth a giant magnet? And the answer is yes, the Earth is a giant magnet. And the compass magnet, or the compass, which is a magnet, the north end, remember, it always aligns itself with the magnetic field. Okay, the north side is attracted to what part of the magnet? Okay, so think about it. The north side is attracted to what part of the magnet? And if you said the north side of the compass is attracted to the south side of a magnet, you will be correct. And so if you think about this and you're thinking, wait a minute, so does that mean that the geographic North Pole is actually the south magnetic pole? The answer is yes. And that is crazy. The North Pole of the compass will always line up with the Earth's magnetic field. And the magnetic field, the way that it's currently operating, is all the vectors are going into the north, the geographic north. Okay, which means that the geographic north is actually the south pole for a magnet. The north geographic pole for the Earth, the Arctic, is actually a magnetic south. I think that's cool. Now, here's another cool fact: the magnetic poles for Earth, they actually flip flop. They swivel around, and that's because the Earth has a molten core in the middle with iron. If you remember back from before, iron is a very strong material for magnetism. We'll get into that later. But there are people that believe that whenever there's a switch in the pole, there's a huge major natural disaster. Some people say that that's where the ice age began, or the dinosaurs died. And fossil records show that that's not the case. I think it was 750 years ago, 750,000 years ago was the last time the poles switched. We have fossil evidence of that. And so we don't have to worry about the next shift, but I think it's pretty cool, right? And it's also important to know that the geographic north doesn't align with the magnetic south. It's actually slightly off. Man, science is amazing. All right. So here's a picture from I got from a NASA website. It shows you how the field lines would look like. I believe this is yeah. So we have the north magnetic pole, and we have all of the field lines going in, and so we call that magnetic south, right? Yeah. All right. So if we are asking ourselves, Mr. Lee, this is all really cool, but what makes a magnet? Okay. And the way that we can answer that is by taking a look inside of the magnet. If we take a look at inside of a magnet, we see these things called domains. So each of these little cells almost is what we call a domain. And inside of a domain, we have the magnetic domain. Okay. So this is north going up, this is north going to the right, this is north going up, this is north going to the left, and it's all over the place. And when it's all over the place like that, the object is unmagnetized. Okay, and it's unmagnetized because all of the north poles are canceling each other out, right? So for example, this north pole gets canceled out with this north pole because we have one going up and one going down. The magnetic fields cancel each other out. But if we have a magnetic material, most of the domains, they line up. And so the north pole goes into the south, which goes into the north, which goes into the south, which goes into the north, which goes into the south, right? And so we create a additive, a summative effect. So all of the north poles, they build on top of each other. Right? And these are caused by the unpaired electron, right? So if you remember from chemistry, we did the upspin and the downspins, and sometimes there were elements that only had one upspin, and it wasn't paired. And those unpaired electrons, okay, once again, electrons in charge, right? We'll get into that, but they have a strong connection. The unpaired electron that's spinning around and around create this really cool magnetic effect, and that's what causes these domains. Okay. All right, and so here we have a picture of a electron that's spinning, and we'll learn how to read the magnetic poles using our hands. We call it the right-hand rule and the left-hand rule. But we have a electron that is spinning counterclockwise. So when it's spinning counterclockwise, this has a positive spin. Okay, and when this is spinning clockwise, it looks like it has a negative spin. And so these are two electrons, and they're paired up with each other. All right, so if we're doing the Pauli exclusion principle, there's an up spin next to a down spin. So we have two spins that are attracted to each other. All right, so the magnetic fields, they cancel each other out. But if we only have one of these, right, if we only have one up spin, so it'll be this one. If we have only one up spin, that means it's a lone magnet, and it's not paired with anything else. And what that means for us is that the material is more likely to be magnetic, and this is especially true for iron. Now, there are materials out there with unpaired electrons that aren't, that are not magnetic, and that deals with how the electrons and the materials want to group up with each other. But that's a video for another day. All right, next up, we had this concept called the magnetic dipole. All right, so magnets always have two poles. It'll always have a north pole and it'll always have a south pole. And the idea is that within the bar magnet, this north pole has a south pole here, and this south pole has a north pole here, and that north pole has a south pole here. And so if we were to chop that magnet in half, we have two magnets. We have a north side and a south side. Okay, and if we do this an infinite amount of times, we still will have a magnet with a north and a south. Because no matter how many times you divide it, you will always have a north side and a south side. And that's what we call a dipole, di meaning two, Latin prefixes. And so you might be scratching your head, but what if? What if, Mr. Lee? What if there is a regular pole? And I'll tell you, well, in the physics community, we don't call it the regular pole, we call it a monopole. All right. So monopoles are very unique. And if you find a monopole out in nature, whatever you did to find it, record it, write a paper, publish it, get other scientists to replicate it, and boom, you'll be in textbooks for the rest of your life. You'll be famous and you'll have money. But knowledge is power, and that's what you should be in pursuit of knowledge. All right, so monopoles. So monopoles are magnetic materials that only have one pole, either south or either north. Scientists have made materials that act like monopoles. Okay, so they're not true monopoles; they just act like monopoles. And the idea is that monopoles should be out there. And we, as physicists and scientists, have not been able to find a monopole, no matter how hard we try. Okay, every time a scientist says, "I did it," right? We try to do it again. We can't find it, and so it's very elusive to us. So you might be asking yourself, why does it matter? The monopoles matter because the whole idea of how linked it is to the electric charges. Okay, scientists are very enthralled with the idea of symmetry. Now, you've heard me talk about electric charges before. The electric charges, they do have monopoles. You can either have just a single positive charge or a single negative charge. And magnets are so closely linked to electric charges that it only makes sense that if electric charges have it, the magnets should have it. And so there's theories out there saying that monopoles first existed many years ago, like at the beginning of time or at the beginning of the creation of the universe. It requires so much energy, or that monopoles are like out there right now. We just don't know how to find it, and just like hiding in plain sight. And there's like other mathematical equations. If we have a monopole, it has enough energy for like 100 mosquitoes flying at your face or something like that. But yeah, monopoles, they do not exist. Keep that in mind. Yet. So that's the key word, yet. Like there's theories out there. There's equations to show us what it would be like, but we haven't been able to find one in nature yet. Anyways, I hope you enjoyed this video. Please take the time to look over how to draw the magnets. We'll be doing a lot of drawings in class, and I'll see you next time when we talk about how the electricity unit and the magnetism unit, they are one and the same.